All right, so what we're going to do today is we're going to look at some applications of the dot product and the cross product. And these are not the applications that are going to be the big focus for us for the last big section of the course, okay? But they're just to introduce people to how these things can be applied, and also how some of them are related to things that you would have seen in physics that now we're giving, we're referencing some of these new operations that we've learned, okay? First on those, first couple are geometric things here. So it says, think back to work on projections. Okay, so hint, hint, the idea of projections will come into play. It says, use the diagram to determine a geometric interpretation of the magnitude of the cross product. All right, so let's think back to what our diagram looked like, and then I'll give you some time to work on it. Okay, so if I draw an exemplar of what we did, and again here, just assume any two vectors. Okay, so we had, say, vector u and vector v, and if we were projecting vector u onto vector v, okay, we had this portion here. Now, if I want to think of this, I'll give you a bit of a hint here. If I want to think of this necessarily as a length, okay, which means that if the vector u was at larger than a 90-degree angle, it could very well be that the projection was negative. So what do I do with a projection to ensure that it's representing the actual length? So I've got here, this is the, scalar projection of u onto v. And what's the only thing I have to do to ensure, there you go, is I just take the absolute value of that scalar projection. So in this case here, the scalar projection is already positive, but if it was going in the other direction, it would be negative. Okay, and we know that that's given by, the magnitude of u times cos theta. And we were able to determine how we could write this in terms of a dot product. So we don't actually need to know theta. All right. So what I'm asking you to do is think about that geometric definition of the cross product and see if that geometric definition of the cross product gives you some information about this diagram. Okay, I want to try to keep it as vague as possible. Okay, but think about what you find in the geometric definition of the cross product. You find the sine theta. Okay, so what does that represent on this diagram? And what does the full definition of the cross product represent? Which, of course, let's keep in mind what that's equal to. Remember that that geometric definition of the cross product is that the magnitude of the cross product is equal to magnitude of u times magnitude of v times sine of theta. Okay, so just give you a bit of time to kind of play around with this diagram and see what you can come up with. All right, so we'll give you about maybe a minute or two. We'll come back and see what we can come up with. Okay, so give it a go. Okay, so we're back. So I guess the first thing here is I've got this sine theta, okay, and then of course I've got the magnitudes of u and v. So can you see anything on this diagram here that would involve that sine theta? Okay, so let's kind of start with how I might incorporate that sine theta into this diagram. Okay, so here we saw that when we took the magnitude of u times cosine of theta, we got this length here. All right. Where might that sine theta come into play? Can anybody see it? Okay, so the dotted line is the magnitude of u times sine theta. Well, yeah, because you think here, this is the opposite side to theta. This is still the hypotenuse, or the magnitude of this vector is still the hypotenuse of this triangle. So you realize that this length here is the magnitude of u times sine theta, which is at least part of what's in this expression. Now, the question is geometrically, what does this dotted line represent? This dotted line represents something geometric here, okay? And the hint is I'm going to be adding something to this diagram, something we've added to this type of diagram when we had two vectors placed tail to tail. What was sort of a useful, if I say the word shape, it's going to kind of give it away, but I guess I'll use the word shape. What shape came into play when we put two vectors tail to tail? Okay. Well, we could connect them, okay, by, there you go. And lo and behold, what have I created if I connect them? Okay. Well, let's say I just connect the two tips. I create a triangle. Or I'm noticing another suggestion is that if I look at the parallelogram created by these two vectors, okay? Now, whether I look at the parallelogram or I look at the triangle, what does this dotted line represent with respect to either that triangle or that parallelogram? There you go. It's the altitude or the height, okay? So it looks as though this expression here represents the height, say, of the parallelogram. And what does, wait a minute, there's also this magnitude of v, which is hanging around. What does the magnitude of v represent in this diagram? There you go. It represents the length of the base. Okay? So here, this magnitude of v represents the length of the base of the parallelogram or the base of the triangle, and this here represents the height of this parallelogram or the triangle. So if I stick with this expression as I've written it and I do a little rearranging, which of course these are just numbers, so they're all commutative. Of course I can do this, and I rewrite this as magnitude of v and then times magnitude of u sine theta. You realize that we have the base of this parallelogram, and this represents the height of the parallelogram. And of course, multiply those two things together, and what do we get? What does that give us when I multiply the base of a parallelogram and height? I just get the area. So we realize here that this magnitude of the cross product geometrically, excuse me, just represents the area of the parallelogram. I think I got that right. Okay, produced by u and v tail to tail. Okay, so we see how this parallelogram formed by two vectors just keeps coming back to be useful for us. Now, of course, if we wanted to determine the area of the triangle produced by these two vectors, well, how would I get that? What would be the area of the triangle produced by u and v? Don't think too hard there. Yeah, just divided by 2. It would just be the magnitude of the cross product divided by 2. Okay? So, nice little result. Okay, again, this idea of this representation of these two vectors using the parallelogram came into play when we were talking about addition of the vectors, subtraction of the vectors, and now we see that it's coming into play when we're talking about the cross product of the two vectors. All right, now question for you though. Remember we had that problem with scalar projection could sometimes be negative. Why am I not putting absolute values around u sine theta? Why is that not necessary here? I'm claiming that it's not actually necessary to put absolute value signs around that. You know, when we wanted this to represent a positive number, we had to put absolute value signs around it. Why is that not necessary here? Okay, and this is where you got to think back to your knowledge of trigonometry. Why do you not have to worry about putting absolute value signs around this expression? Since of course you want area to represent a positive . There you go, because remember what theta is allowed to be. Theta is only allowed to be between 0 and 180 degrees, okay? And we know that sine in quadrants 1 and 2 is always positive. And there you go. So that's why we don't have to worry about the idea. And it kind of makes sense. We shouldn't have to worry because, hey, this is supposed to be representing the magnitude. Remember, this represents the magnitude of the cross product. So it turns out that everything's a-okay. We don't have to worry about this ever being negative. All right. Okay, so here's our first result. But if we now have that the area of a parallelogram is given by the magnitude of this cross product, well, it turns out that the parallelogram is one of the shapes, or the shape that we find in a parallelepiped. And in particular, if I have this parallelepiped that's created using these 3 vectors now, okay? Well, now I realize that I have a way of determining the area of the base of this shape, okay? Now, we're not going to prove this in any sort of way, but we're just going to use our reasoning here that the volume of this parallelepiped, well, anybody want to guess what the volume of the parallelepiped is given by? And again, maybe use the parallelogram as inspiration. There you go, the volume of a parallelepiped, like the volume of a rectangular prism, or any prism, in fact, okay? And remember, a rectangular prism is just a special case of a parallelepiped, is just given by the area of the base times the height. And of course, what's important about measuring the height of any shape? Okay, let's keep in mind what is important about measuring the height of a shape. How do I measure the height of this thing here? No, not necessarily. Okay, like a rectangular prism, it doesn't matter which one I call the base. Okay, but there's something very important about the height. There you go. It has to be perpendicular to the base. So even here, when you think about this parallelogram, the height of the parallelogram is given parallel to whatever you're choosing as the base. Had I turned this around and chosen this as my base, then that would have been the height there. Okay, so it's all relative to whatever you're choosing as your base. So if I'm choosing this parallelogram as my base, the height would be given by this here, where it's perpendicular to this. Okay, so what I'm claiming is that we can find a nice formula for the volume of this parallelepiped, like we were able to find a nice formula for this area of the parallelogram, okay? And I do give you a little bit of a hint here, okay? So I'm claiming that somehow a cross product and a dot product can help you determine the volume of this parallelepiped. Now, we already have a cross product, okay? Because we kind of know how you're going to get the area of the base of this parallelepiped, because it's a parallelogram. We just did that above, okay? But how is a dot product going to come into play? So I'm going to give you a bit of time to work on this, but I'm going to draw something else on here that maybe will give you a little bit of a hint, okay? This height here, I'm just going to draw that line off where these 3 vectors, okay? These 2 heights are equivalent, I guess maybe a little higher. That's maybe the hint I'm going to give you. Okay, so take a minute, play with the diagram, see what you can come up with, all right? But the hint is that this process is going to involve not just a cross product, which clearly it's going to have to, because of the area of the parallelogram, but it's also going to involve a dot product. Okay, so let me give you a minute, play with it, see how far you can get with it. Okay, so we're back here. So essentially, our goal is to find a nice way to represent the height of this parallelepiped, because we've already got the area of the base covered, given that it's a parallelogram, and we know how to find. It would just be the magnitude of the cross product of V and W. Okay, so ideas on how we could determine this height. All right, and did anybody come up with something? Sorry, Andrea, we'll try to keep you a bit more excited there. Keep your eyes open there. So, I guess the reason why I drew it here is what I was trying to imply to you is that if you take this vector u, if you could find a way to project a vector u onto the perpendicular line here, because remember this goes at a 90-degree angle, then you'd be able to use projections to determine this height. Okay? Now, the question is there a vector that's easily determined that is perpendicular to the base of this parallelepiped? So can anybody give me a suggestion as to what vector I could use? Okay, so we know that the dot product would be equal to 0, of course, but my question is how am I going to find this vector that's perpendicular to the base of this parallelogram? We have a way of doing that. So think about this parallelogram. It is defined by these two vectors, v and w. There we go. Let's take the cross product of v and w, and what do we know that's going to produce? It's going to produce a vector that is perpendicular to both. This v cross w has to be perpendicular to the base. So look at what we're going to do now is we're going to project the vector u onto the vector v cross w. So this here, and if I want to guarantee that this represents a length, okay, because I want it to represent some positive value, this here is just represented by the absolute value of the scalar projection of u onto the vector v cross w. Okay? But what is the scalar projection given by? Well, hey, we have a formula for the scalar projection of one vector onto another. That's just the dot product of the two vectors. So u dot v cross w. Hey, look what just came into play. Okay, divided by the magnitude of the vector we're projecting onto, which is the vector v cross w. So now look at what we have. We have a formula for the area of the base, the cross product of v and w, and now we have a formula for the height of this parallelepiped. Okay, so let's put everything in there. We know that the area of the base, this parallelogram, is going to be the magnitude of v cross w, and then multiplied by the height, which is given by that scalar projection, u dot v cross w over magnitude of v cross w. And now we can do some simplification. Now I'm taking an absolute value here, okay? But I'm taking that absolute value because the numerator could possibly be negative. So I want to make sure I take the absolute value of that number. But hey, this denominator can never be negative. So I can just remove it from the absolute value because I know the magnitude of v cross w is always going to be positive. So I can rewrite this as u dot v cross w divided by the magnitude of v cross w. And I'm sure you're seeing what's going to happen now. Look at that. These things just cancel out. And all I'm left with is this, what we call a triple product. Okay. Now notice how I'm keeping the absolute value here because this dot product could be negative and I'm looking for some positive value because it's a volume. All right. And this now is a fairly easy thing to calculate because calculating the cross product, nice and easy. We've got practice doing that. And then just a dot product with U, and the absolute value of that number automatically gives you the volume of the parallelepiped. Okay, so another nice geometric result coming from these two operations. All right. Now,
Tony,
yes.
do you not need the brackets around the V cross W anymore?
That's very funny, Charlie, because I was just going to ask that question, because, and certainly I know I make a lot of silly errors here and there, and I could imagine missing one bracket, say if I put one bracket and miss the other. But the fact that I just took the brackets out altogether, well, that's my next question. Okay. Now, one of the homework questions from yesterday, I know it was a late, it's tough, these sort of late lessons that then go into the early lesson on Friday. But if you did get a chance to look at the homework, one of the questions would have given you a whole bunch of these triple products. And they would have said which one of these, are reasonable and which ones are not. Okay? So if you take a look at the triple product as it was written up here, is this a reasonable product to take? Well, let's see. Let's do the bracket first. What kind of object do I get when I take the cross product of the two vectors? What does the end result looks like? It's a vector. And then can I take the dot product of two vectors? Yeah. Okay. So this is a reasonable triple product. Now, in scenarios like this one, and we'll talk about what I mean, you can actually not even put in the bracket. And the idea here is it possible to first take the dot product? Well, let's see. What happens when I take the dot product of U and V? I get a scalar. Can I take the cross product of a scalar and a vector? And the answer is no. Okay, so the reason why I'm allowed to just take the brackets away is because there's only one reasonable way to perform these products. The only reasonable way to perform these products is to first do the cross product, and then that result can be dotted with the first vector. Okay, now by the way, nothing stops you from still writing the brackets. Okay, there's nothing incorrect about that. But just so that you're introduced to the fact that when we have these triple products, if there's only one way to go ahead and operate on these vectors, then we just don't bother with the brackets. Okay. So any questions on these here? Okay, I would say this is definitely a a very classic result. Okay. Let me look at that. Can you do a quick run of why it's a projection of V over V cross W? Yeah, for sure. Okay, so can you see here that this height is the same as the height as if I was drawing it in this direction here? Okay, so what I'm thinking is well, if I could have a vector that's perpendicular to the base, like this line has to be perpendicular to the base, then I could do a projection of vector U onto this vector, which is perpendicular to the base. So the question I have to ask myself, is there a way to easily produce a vector that's perpendicular to both W and V? And the answer is yes. That if I take the cross product of these two vectors, it's going to produce a vector which is perpendicular to both of them. It's perpendicular to both U and both V, hence, sorry, both W and V, hence it's going to be perpendicular to the base of the parallelepiped. So at that point there, I say, oh, let me take my vector U and project it, remember, 90-degree angle, onto this vector here. So this scalar projection is going to be the same as the height of the parallelepiped. Okay, so this is why I project vector U onto the vector v cross w, because the vector v cross w is in the direction perpendicular to the base. Okay? Does that help a little, Ali? Okay. So one thing I will say, by the way, this material is not going to be covered on the quizzes. Okay, this is not material that I would be covering today's stuff in the modified course. Okay, but you know, depending on what you're studying next year, a lot of this stuff could be quite useful. Now, by the way, this parallelepiped idea might look like it's okay. It's a cutesy geometric property, and it is. That's great. But this idea of the triple product will come in very handy for us later on. Okay, so keep in mind that this is not the last we're going to see of the triple product. We're just going to see it in a different context, but a context that is sort of related to the parallelepiped. All right, so the last thing we're going to look at today is a couple of applications to physics. Okay, and I know these, if you've taken physics, you would have already been exposed to these ideas. Okay, so if not, just give a thought to these questions and just, make a conjecture as to what you think might happen. Okay, so we're going to define this idea of what it means to do work. But what I'm giving you is I'm giving you 3 examples, and I just want you to think, intuitively. So if, like I said, if you've taken physics, you kind of know exactly where this is going. If you haven't, just try to think intuitively. What do we mean by doing work? Why are these 3 why would these 3 scenarios be different if you're applying the same force to something? You're still applying the same amount of force to each of these, in each of these scenarios, to this cement block, yet I'm giving you the tip here that what we mean by work is going to be different in the 3 scenarios. Okay, so take a minute or 2 to just kind of look at that, see what you come up with, and then we'll come back and come up with some details. All right, we're back. So let's just not even give numbers here, but let's just think. Okay, has Felipa done work? Okay. Has Felipe done work? Okay, we got a few no's here. Has Filippo done work? Ah, he has. Okay, so who's going to tell me what's the difference between what's happening in A and C and what's happening in B? So what is the main difference? Okay, because all we talked about is whether they did work or not. We'll talk about how much work they performed. Okay, so we see that in A and C there's displacement, and then B there's none. Okay, and so work, when we talk about, I'll make a bit of a life example here, and they tell you, if you don't, if you're playing football and you set up a good play and it just so happens that, the receiver misses the ball, and the coach might tell you, hey, good work, you tried your best. Unfortunately, physics isn't quite so generous, okay? Because when it comes to work, you're only considered to have done work if you've actually produced a motion in the object on which you're applying the force. Okay, so in this case here, despite the fact that you're, trying to pull this this pickup truck and you're applying this force of 300 newtons, you might be sweating just as much as when you're applying the 300 newtons in the other 2 scenarios. If you haven't actually moved the object, you're not considered to have done any work. Okay, whereas in these 2 scenarios, you have sorry, say that again. Oh, sorry, I'm missing some of these here. A and C both have component of direction of motion. Okay. So here in these two scenarios, you have moved the object, and you have moved the object by 2 meters, okay? But have you done the same amount of work? Okay, so this is where we're going to come into one of the other comments. Have you done the same amount of work in A and in C? Okay, and the answer is no. Because in terms of the force that's being applied, you're only interested in the portion of the force that's in the direction of motion. Okay, so if you have, this case here, you have the force which is being applied parallel to the ground, and it's being moved by 2 meters. Okay, I guess this is, we'll call this the displacement vector, or you call it as a vector instead of just its, okay. And so here we see that the force and the displacement are in the same direction, whereas here you have the displacement, which is still 2 meters, let's assume horizontally, and then here you have the force, which is 35 degrees from the ground. All right. So which one of these two did more work? So who's going to tell me which one did more work? Okay. Well, let's take a look. So if we take a look at these two here, what is the force in the direction of motion? Well, this is great. We got lots of different answers here. Okay, so the force in the direction of motion. So here, work is equal to the force or magnitude of force in direction of motion. Okay, times the magnitude of the displacement, which is just the distance traveled. Okay, so here, let's take a look. We see that the force, magnitude of force is 300, and then what is the displacement? 2 meters. Okay, and so here we have 600. Okay, now you got force that's given in newtons, and then you've got distance that's given in meters. So you've got Newton times meters, and we actually give this as another name, and we see that somebody's bringing it up. This is what we refer to as joules. Okay, now we need to be very careful here, because we're going to see this Newton times meters come up in another context, and it's not going to represent this idea of joules. Now, when you think of joules, what do you think of? What's the unit that's normally associated with? That's it. You think of joules as being associated with energy, and there is a relationship with work and energy. And I don't want to go into this very much, because we're just looking at this as a simple example of one of our operations. We'll see in a second. Is you think of work as some sort of transfer of energy. Okay. So here there's a transfer of energy from the force that's being applied to, say, the heat of the friction, to the kinetic energy of the object. Okay, so it makes sense that this refers to joules. Okay, so let's take a look here. Well, what is the force in the direction of motion? Is it still 300 newtons? No, because the direction of motion is going to be only the horizontal component of this force. Okay, now we've seen this many times. We know that the horizontal component of this force is just going to be the force 300 times, in this case here, because it's the what do you call that? Adjacent side is just going to be cos of 35. Okay, so this is the force in the direction of motion, and then it's still moving 2 meters. But wait a minute, what can you tell me about cos 35? What can you tell me for certain about the number cos 35? Okay, it's definitely less than 1. Okay, so even though this person is still applying the force of 300 newtons, it's actually considered to be done less work. Okay, and I guess you can think of it in the fact that this was not done as efficiently as it could have been done. Okay, the most efficient way of applying this force would be parallel to the direction of motion. Okay, so the full amount of the force is being used to produce that displacement, whereas here it's only a portion of that force that is actually going towards producing the displacement. So Filippo actually does less work than Felipe did. Okay, very good. We even have a, okay, the important thing is here, less than 600. Okay, great. So now this is where I'm hoping that in looking especially at this example, okay, that you might see something familiar, because it looks as though here you have the magnitude of the force that's applied. This is the magnitude of the displacement, just the distance traveled, and this is the cosine of the angle between them. So what should we be thinking of when we see these two magnitudes and the angle between them all being multiplied? What happens when I multiply? There you go. And you realize that the work that is achieved, all right, is just given by the dot product of these two vectors. Okay. Now, obviously, in one dimension, you don't have to think about this. Work is just, you know, force times distance, and that's it. It's done. Okay. Whereas here, when we're in 2 dimensions or 3 dimensions, we need to bring in this idea of that component of the force in the direction of motion, which is not necessarily the same as the direction of the force itself. Okay, and we see the dot product perfectly represents this. Now, if you're only working with geometric vectors, okay, you don't really need to think of this in terms of dot product, because you know you'll have the angle, you'll be able to find the angle between them, and you won't have to worry about that being an annoying part of the work. Okay, whereas if you're working with algebraic vectors, well, you definitely would prefer not having to work with the angle between the vectors. Okay, so in general, if you have some force, okay, that is producing some displacement, okay, so you know that the work, which we said was given by the magnitude of force in direction of motion, motion times the magnitude of the displacement, or the distance. Well, we can see here in our diagram that the magnitude of the force in the direction of the motion is just the magnitude of your force vector times the cosine of the angle between them, okay? And the magnitude of your displacement is just the magnitude of your vector d, the distance traveled, and of course you do a little moving around and you get magnitude of f times magnitude of d times cosine of theta, which of course is otherwise known as f dot d. Okay, and so this is how you can calculate the work. So notice here that work is a scalar quantity. Okay, it's not a vector quantity. So that's sort of works that it's defined by this dot product. Okay, and depending on the way the information is given, so if you look at the next 2 examples, you're going to see that in one example, the information is given geometrically, so you're likely to work with the geometric definition of the dot product. But if you look at number 6, the information is given algebraically, so you're much more likely to work with the algebraic definition of the dot product. Okay. So what I'd like you to do is I'd like you to take a look at these two questions. Okay, I'll give you maybe, so it looks like we're going to end off here, which is fine. I'll give you maybe till 9:55. All right, we're back. So let's take a look at these two things here. Okay. Did you notice that this question had some unnecessary information? Is there any info that you didn't end up using? Yeah, you kind of realize, and I figured I'd throw that in since I believe they do that in physics all the time, right? They give you some piece of information that doesn't end up coming into play. So in the end, if you're trying to represent this here, so you got the box that's going up the ramp and then horizontally on the top. And in the end, the direction of motion is always given, or sorry, the direction of the force is always given with respect to direction of motion. So this is 20 degrees, and here moving this way, the displacement, but the force is again given with respect to the direction of motion. So you never actually need the incline of the ramp of 12 degrees, okay? Now, I could have easily have given this question where the forces are all given with respect to the ground, in which case, this would have been not an angle of 20. I guess it would have been an angle of 32 if I was giving it always from the horizontal, okay? But in this case here, we didn't actually need it. So here they want the total work done. So what I think best to do is to split it up into the work done going up the ramp and the work done going along the edge, because we don't have exactly the same force in both cases, okay? Because there's only half the magnitude being applied when you get to the top of the ramp, okay? So if I think here is this being, actually, let's write it out using the formula. So if I think of this as F1 dot D1, and then I'm going to add to that F2 dot D2. Okay, let's see what we get. Well, we get the magnitude of F1 times the magnitude of D1 times cos theta, and then I guess theta 1, and this is the magnitude of F2 times the magnitude of D2 times cosine of theta 2. Okay, and so here, what do we have? We have, I guess it's 90 times, here it's what, 10 meters times the cosine of 20 degrees. And here we've got the force, which is only half as much, so 45 newtons times, what do we have here? 15 meters times the cosine of still 20 degrees, because it's always 20 degrees from the direction of motion. Okay, and I got here 1480. We good? Is that what people got? Check my work. 1480 joules. Yeah, there we go. All right, and so there you have it. This is the amount of work that was done. All right, now for this one here, okay, I'm hoping you might have remembered a question or a solution that I gave you for something in the quiz we did, not one of the official quizzes, but one of our unofficial quizzes, okay? So first of all, I would say the easy vector to determine, so I'm gonna try to, I don't wanna work with an angle here at all. I wanna keep this completely to algebraic vectors. And I think the easy one for sure is the displacement, because what am I doing? I'm going from point P to point Q, and so the displacement is just going to be the vector that joins those 2 points. And of course, we know that we find that by just subtracting second minus first. So 5 minus -2 is 7, 6 minus 1 is 5, and 3 minus 0 is 3. Okay, so there's the displacement vector, nice and easy. It's the force vector where we have to do a little bit of work. Okay, now you could certainly solve an equation to find the vector that's in the direction of 1, 1, 1 and has a magnitude of 10 newtons. So we can see very easily that this vector that gives us the direction does not have a magnitude of 10 newtons. So can somebody give me a quick way to get this vector without having to solve an equation? Okay, what trick did I use in that question from the quiz? Where again, I could solve an equation for sure, no worries about that, but what was a way to determine this vector very easily and quickly? What could I do with this vector 1, 1, 1, which is just representing the direction of the vector? Try to think, how can I create a vector that's not going to contribute to the magnitude? There you go, is to use the unit vector. So if I call this, say, vector u, okay, what I'm going to do is I'm going to take vector u divided by its magnitude. That's going to give me the unit vector. And then if I need that to have magnitude of 10, if this magnitude is just 1, what am I going to do to this vector to have it get a magnitude of 10? Just multiplied by 10. Okay, and again, this is that nice usefulness of unit vectors. So here, the vector that represents the direction of the force, I'm just going to use this unit vector, which is just going to be 1, 1, 1, divided by its magnitude, which is just going to be square root of 3. Okay, so the force vector is just going to be equal to 10 times this unit vector, 1 over root 3, 1 over root 3, 1 over root 3, which is just 10 over root 3, 10 over root 3, 10 over root 3. So this is much faster than solving an equation. So now when I want to find the work, that's just equal to F dot D. I'm not going to bother writing that out since we have it here. So what's that going to give us? It's going to be 70 root 3 plus 5 times 10 over root 3, 50 over root 3, plus 10 over root 3 times 3, 30 over root 3. So this is going to be equal to, what is this? 150 over root 3 joules. Okay? And I could certainly, find an approximation for that. Okay? So just to recap here, we dealt completely out geometrically because that's how the information was given, whereas here I dealt completely algebraically because, again, that's how the information was given. So I know I'm going a little over time, but let's just take a quick look at the notes to recap here. Okay, so area of a parallelogram given by two vectors, and I notice here non-collinear vectors. I think there's in fact a question in the homework that kind of makes you think about, why you might not want to consider this if u and v are in the same direction. Okay, and of course, if you want to just find the triangle created by those two vectors, it's just half of that. We saw that the volume of the parallelepiped given by this triple product of the dot and cross product. Okay, we talked about this idea that these triple products, if there's no brackets, you just do it in whatever order is reasonable. So here, it's not reasonable to first take the dot product and then a cross product. So that's why you have to do v cross w first. And here's an example where you realize, hey, this doesn't make any sense at all, because if I take u dot v, I did a scalar, I can't do a scalar dot a vector. Or again, if I do v dot w, that's a scalar, can't dot a scalar and a vector. Okay, and then we have this idea of work, which is given by the dot product to two vectors. And next class, we'll take a look at this thing called torque.